Okay, hello, this is chapter 18, and in this chapter we're talking about extraction of metals. How do they make metals on a large scale? So when we make metals, metals are extracted from what we call their ores. The ore is the raw form of the metal obtained from the earth. So in order to get a metal, aluminium or sodium or zinc or iron, I need to get something from the earth, a raw form of the metal from the earth, and then I can work on it in order to get the metal. So that is what we call the ore. The ore is the raw form of the metal obtained from the earth. Now, which method of extraction should I use? I have two different methods of extraction. I can either use electrolysis or I can use reduction of the oxide using something like carbon or coke. Now, which method do I choose depends on the reactivity of the metal. You remember the reactivity series? Now, some metals which are at the top are very reactive. The metals at the bottom are less reactive. And we put a carbon and carbon monoxide in the middle. Can you see that? Now, anything above carbon or carbon monoxide has to be made by electrolysis. So the very reactive metals like sodium, aluminium, they have to be made by electrolysis. They cannot be made by reduction with carbon. So I cannot bring magnesium oxide and react it with carbon, because carbon is less reactive. It will not displace the magnesium. I cannot say aluminium oxide plus carbon, because carbon is less reactive, will not displace the aluminium. But the metals that are less reactive than carbon are extracted by reduction of their oxides by coke, which is carbon. Okay, so the method that we choose depends on which metal we're trying to extract. So let us talk about extraction of aluminium. You should know that the main ore of aluminium is something called bauxite. So this is what I'm going to make aluminium from. Bauxite is a substance that is obtained from raw form in the earth, and bauxite is actually hydrated aluminium oxide. So this bauxite or hydrated aluminium oxide, the first thing that we do is remove the water. So I heat it in order to get just pure aluminium oxide, which is Al2O3. This is also referred to as alumina. And then I take this and do electrolysis. So in electrolysis, we said, if you remember what we said about electrolysis, that means I need the aluminium oxide, but I need it to be molten. I need to heat it until it melts. Now I have a problem. In heating aluminium oxide until it melts, I need to heat it to 2100 degrees centigrade in order to melt it. That is a very high temperature and it requires a lot of energy, so that is actually very expensive. So they tried to add some sort of impurity to the aluminium oxide in order to melt it at, remember when we add impurity to something, it melts at a lower melting point. So adding any impurity will lower the melting point of the aluminium oxide, and they kept trying until they found something called cryolite. When you add cryolite to the aluminium oxide and then try to melt it, it will melt at only 900. So that is much lower than 2100. So why are we using cryolite? To lower the melting point of aluminium oxide, because if I need to melt it to heat it to a lower temperature, that means it is less expensive. It's using less energy. So my electrolyte that I'm going to do electrolysis of is actually a mixture of the molten aluminium oxide and cryolite. Again, why are we adding cryolite? To lower the melting point of aluminium oxide. If he needs another reason, it is to act as a solvent for the aluminium oxide. It's as if you're dissolving the aluminium oxide in the cryolite. Now, the electrodes that we're going to use are made of graphite, which is carbon. And this is the kind of setup that you have. So the positive and negative electrodes are made of carbon or graphite, and the electrolyte is a mixture of what? Aluminium oxide and cryolite. Now, what will go to the cathode? The aluminium ions will go to the cathode, take up electrons and become aluminium. So the aluminium is collected at the cathode. Now, what happens at the anode? We have aluminium oxide. That means we have aluminium ions and oxygen or oxide ions. The oxide ions are negative, they go to the positive. They go to the positive and do what? And give electrons. But this forms oxygen gas. Now, I'm giving out oxygen gas at an electrode that is made of carbon, then the carbon will burn. That means the electrode itself, the anode, the positive electrodes that they put into the electrolyte will start to burn and give out carbon dioxide gas. So they will be used up from time to time, and we have to remove them and replace them with new anodes. So if he says, why is it that the positive electrode has to be replaced from time to time? Because the carbon in the graphite burns with the oxygen that is formed at the electrode to form carbon dioxide gas, which is released. So this is breakdown of the graphite. What do we use aluminium for? So we've made aluminium. What do we use it for? Actually, aluminium is one of the most useful metals that we use, and you have to know it is used for what, because of which property. So for example, we use it to make food containers. Which property does it have to allow us to use it as food containers? Aluminium resists corrosion. And if I say, why does it resist corrosion? Aluminium is a metal. If you expose, and it's a relatively reactive metal, if you expose it to the air, it will react with the oxygen in the air. And this forms aluminium oxide. But then this layer of aluminium oxide covers the aluminium. So it prevents it from any further reaction. So if we say, why is it that aluminium resists corrosion? That is because it is covered with a protective oxide layer. It is covered with a protective oxide layer. So I use it in food containers. Why? Because it resists corrosion. It is not poisonous. It doesn't form any poison substances. And it does not react with food. Also, it does not react with food because it is covered with a layer of protective or a protective oxide layer. We also use aluminium for overhead cables. Do you know what are overhead cables? These are the electric wires that are carried on poles outside in the streets or in the fields or anything. So these are called overhead cables, the electric wires that are carried on poles. So in order to make overhead cables, I need a metal that conducts electricity, but that is low density or light, so that I don't need to put a lot of poles in order to connect electric wires from one city to another, for example. So I use aluminium for overhead cables. Why? Because it has low density and it's a good conductor of electricity. I also use aluminium to make aircraft bodies. The bodies of airplanes are made of aluminium. Now, why is it that I can use aluminium? Because to make airplanes, I need something that is not very heavy. So aluminium has low density. And I need something that is strong to withstand pressure. You know that when the airplane goes up in the atmosphere, there is a strong pressure on it. So it has to be, or high pressure on it. So it has to be strong in order to withstand pressure, and it has low density, or it is light. We also use aluminium for cooking utensils. Why do we use it for cooking utensils? Because it's a good conductor of heat, and it will not react with the food because it has a protective oxide layer. Okay, the other metal that we need to know the extraction of is iron. Now, remember that each metal, we said, is extracted from its ore. Do you remember what was the ore of aluminium? The ore of aluminium was called bauxite. Now, the ore of iron is called hematite. Can you see the word hematite there? Hematite is the ore of iron. So, now iron in the reactivity series is below carbon. So, it can be displaced by carbon. And that means I don't need to go through the expensive process of electrolysis. Aluminium, we have to extract it by electrolysis because it is more reactive than carbon and will not be displaced by it. But iron, I don't need to do electrolysis. So I can just put the iron oxide, hematite is iron oxide. So I can put the iron oxide with coke and it will be reduced. So what they do is they do this in a huge furnace. This is called a blast furnace. So this is actually a huge building a huge furnace called the blast furnace, and at the top of the furnace I put the things that need to react. Now, what do we put into the blast furnace? We put three things. We put coke, which is actually a form of carbon. We put limestone, and I will tell you that limestone is actually calcium carbonate, and hematite, which is the ore of iron, and it's actually iron 3 oxide. Okay, so let's see what happens in the blast furnace. You put at the top the coke, the limestone, the hematite, and from the bottom you pass hot air into the blast furnace. Can you see where the hot air is going into the blast furnace? At the bottom of the blast furnace there is hot air going in. So the hot air goes up, it meets with the coke and the limestone and the hematite, and you start to get reactions happening. Now, what are the reactions that happen in the blast furnace? The first reaction is the coke, which is carbon, reacts with oxygen from the air to form carbon dioxide. So basically the coke is burning inside the furnace to give carbon dioxide gas. Now, this reaction is very exothermic. Again, exothermic means it gives out heat, so it raises the temperature of the furnace, and this is good. I need the temperature of the furnace to be hot. So what is the use of this first equation is, or what is the importance of this first equation is that it is very exothermic and helps to raise the temperature of the furnace. Or he could ask you which reaction helps to raise the temperature of the furnace? That first one, where the carbon burns in oxygen to give carbon dioxide. But then you have a lot of coke around. So when this carbon dioxide is formed, it's actually reduced again by the coke, which is carbon, to give carbon monoxide. So what actually reacts with the hematite, and we said the hematite is iron 3 oxide, so the hematite is the Fe2O3. The Fe2O3 will actually react with the carbon monoxide to form iron and carbon dioxide. So the carbon monoxide is the reducing agent. This is what is reducing the iron oxide to iron. So the carbon monoxide is the reducing agent in the blast furnace, and this is the reaction that happens. It changes the iron oxide into iron, and it itself changes into carbon dioxide. So at that point, I have formed iron. Now the iron goes down to the bottom of the furnace. All of this is very hot, so what I have is actually molten iron. Can you see the molten iron at the bottom, very bottom of the furnace? That is the iron I have just collected. But then I had put something else that I haven't mentioned. Remember that we put at the bottom of, at the top of the blast furnace, what did we put? We put coke, limestone, and hematite. I have used the coke because that's the carbon. I have used the hematite, and that's the iron 3 oxide, but I haven't used the limestone. Why did I add the limestone? I add the limestone to remove the impurities that are present in my ore. Now, remember that my ore is something that I got out of the earth. So the main impurities would be sand. When you go and dig up something from the earth, it comes out with a lot of sand in it, or a lot of soil, and so on. The sand in chemistry is what we call silicon dioxide. So I put the limestone, and we said limestone is calcium carbonate. You are putting it into the furnace, which is very, very hot. The calcium carbonate breaks up to form calcium oxide plus carbon dioxide. Of course, the carbon dioxide gas, if you remember the furnace, let's go back to the furnace. Can you see the opening at the top that says waste gas? So any gas that is not required in the blast furnace will go out from that top opening. So carbon dioxide can either be used again or it will just go out. And I have now lime, which is calcium oxide. Now it is the calcium oxide that reacts with the sand, or what we call silicon dioxide. When these two react, they form something called calcium silicate. Now my first question is, why do you think these two react? Calcium oxide is a base. What do you think is silicon dioxide? If it reacts with the calcium oxide, the silicon dioxide, if you remember, is an oxide of a non-metal, so that is an acid. So the calcium oxide, which is basic, reacts with the silicon dioxide, which is acidic, to give a salt. There is no water because we don't have any hydrogen in our reaction anyway. So the calcium silicate is what is formed, and we call the calcium silicate slag. Do we understand this? So why did we put limestone? To remove impurities. What happened to the limestone? The limestone, which is calcium carbonate, breaks up to form lime, which is calcium oxide, and it is the calcium oxide that reacts with the main impurity, which is sand, silicon dioxide, to form calcium silicate. Now, the calcium silicate is called slag. Let me go back to the diagram. Can you see where molten slag is? The slag floats on top of iron because the iron is heavier. So the iron that was formed from the blast furnace, from the reduction of the hematite, goes down at the bottom. So that's molten iron. And then the slag that is formed from the reaction of the limestone with the sand floats on top of this. Now, the slag has two functions. Actually, in the blast furnace, it floats on top of the iron. Now, when it floats on top of the iron, that prevents the iron from reacting again with the oxygen in the air at the top of in the blast furnace and becoming reoxidized. I don't want my iron that I formed to return back to iron oxide. So the function of the slag in the blast furnace is that it floats on top of the iron to prevent its reoxidation. But then after I have finished all of this, I can remove the slag and it is used in road making. Do you remember one other thing that we said is used in road making? Remember when we were doing fractional distillation of crude oil or petroleum, the lowest thing that we had was bitumen, and we said bitumen is used in road making. Slag is also used in road making, which is calcium silicate. Okay, now this iron that we got out of the blast furnace is not pure. I still need to purify it to change it into something we call steel. Steel is actually a mixture of iron and carbon, but I have to add specific amounts of carbon to make specific types of steel. So first of all, I want to purify my iron so that it doesn't have anything in it, and then I can add whatever I need in the specific amounts in order to make whatever steel or type of steel that I need to make. So this iron that comes out from the blast furnace is the molten iron. I put that into another container, a huge container actually, and I put it in the form of molten iron. It's just coming out of the blast furnace. It is molten. I put it. And then I pass through this molten iron. I put two things. I put calcium oxide and I put hot oxygen through it. So I'm bubbling hot oxygen through this. Why am I bubbling hot oxygen through it? In order to oxidize the impurities. Now, what are the impurities that are in the iron? The iron was from the blast furnace, and we had a lot of coke in the blast furnace. So one of the impurities is carbon. And the other impurity is sulfur. Now, where did the sulfur come from? Because the coke that I used in the blast furnace has sulfur impurities. Coke is carbon with some sulfur impurities. So when you pass oxygen through this iron that came out from the blast furnace, it will oxidize the impurities. Now, what are the impurities? We have the carbon from the coke, remains of coke in the iron, will be oxidized to carbon dioxide, and that's a gas, and the gas escapes. Good. The sulfur, which was originally an impurity in the coke that we used, will form sulfur dioxide. That is also a gas, and that will escape. Good. But what other impurities do we have? We have other impurities that will form oxides that are acidic. So things like phosphorus or silicon will form acidic oxides. So I add the calcium oxide, which is a base, in order to react with acidic impurities, and this forms also what we call slag that floats on top of the iron, and it can be removed. Now I have pure iron. I can take this pure iron and add whatever amount of other substances such as carbon or nickel or chromium in order to make specific types of steel, which we will be talking about. So this is a typical question on this kind of extractions. The question says iron is produced in a blast furnace. Give the common name of the iron ore. What was the ore of iron? Hematite. Its name was hematite. Explain the role of the hot air in the furnace. Why do we pass hot air from the bottom going up into the furnace? To provide oxygen, which will oxidize the coke to form carbon dioxide, because that goes on to the next step. Name the gas that makes up the highest percentage of the waste gases. Let's think about this. First of all, when we had reactions in the blast furnace, we formed carbon dioxide. Okay. And we also said that we will form carbon monoxide. Okay? But then the air is mostly what? Do you know what is the gas that is present in highest percentage in air? Nitrogen. Air is mostly nitrogen. It's about 79% nitrogen. Did we use this nitrogen for anything? No. So the gas that makes up the highest percentage of the gases coming out is nitrogen. It will have some carbon monoxide, it will have some carbon dioxide, but actually it's mostly nitrogen because the nitrogen was there 79% and we didn't use it. Okay, carbon monoxide is the main reducing agent in the blast furnace. Explain how carbon monoxide is formed. Where did we get carbon monoxide from? We said the coke that we put in reacts with oxygen from the air to give carbon dioxide. And then this carbon dioxide is reduced by coke to form carbon monoxide. Right? Write the chemical equation for the reduction of the hematite by carbon monoxide. We said this plus carbon monoxide to give iron plus carbon dioxide. And when you sit down and balance it, you'll find that it needs this type of balancing. You should know how to balance by now, I hope. Okay. Alloys are something that we need to talk about. So we were talking about steel, and we said, what is steel? We said steel is iron with something added to it. Now, when you have a metal and there is other things added to it, that's what we call an alloy. So alloys are mixtures of metals with other elements. They could be metal with metal or metal with things like carbon and so on. So this is called an alloy, but you must have at least one metal in the alloy. So alloys are mixtures of metals with other elements, and this is formed by mixing the molten metals together and then allowing them to cool. So I have molten iron and nickel and chromium and whatever. I heat them until they melt and then allow them to cool. If you remember, the metals had, any metal has regular rows of positive ions. All of these are positive ions. All of these are positives. If the plus is not clear, all of these are positives. And they are surrounded by delocalized electrons. This is a normal metal. But when I say it's a mixture, that means you have different types of positive ions. So some positive ions are bigger than the other positive ions, and that means that you're basically disrupting the regular rows of positive ions. So this is the diagram of an alloy. Alloys are stronger and harder. Something that you have this diagram of would be stronger and harder. Why would it be stronger and harder? Because you're disturbing this layers of positive ions. So the layers of positive ions cannot slide over each other easily. Remember that we said normally metals are malleable and ductile because the layers of positive ions can slide over each other. But when you have positive ions of different sizes, then it is difficult for the layers to slide over each other, so that makes the alloy harder. So remember that when we add something to the iron, for example iron, and I add to it carbon, the more carbon I add, the harder the metal becomes. Now when I have an alloy of iron, that is called steel. So I have steel is something that has iron and carbon, and it may also have things like nickel or chromium. And as the amount of carbon increases, the steel becomes harder. So the types of steel that we have could be mild steel, high carbon steel, stainless steel. Each of these can be used for, have special uses due to their hardness or due to their properties and so on. So mild steel is something that has a low amount of carbon, and this is used for making car bodies, machineries. That is mild steel. High carbon steel is something that has more carbon, so it is iron with a lot of carbon. This would be harder, so it is used for cutting tools and machinery that needs to be much stronger. Now, stainless steel is actually iron and carbon and chromium and nickel. Do you understand that? Stainless steel is iron and carbon and chromium and nickel. This is more resistant to corrosion. This doesn't corrode easily, so we use it in making cutlery. Do you know what's cutlery? Cutlery is your spoon and fork and knife that you eat with. Okay, so that's copper. Okay, we can also have alloys of copper. Alloys of copper. There are two types of alloys of copper, something called brass and the other is called bronze. If I mix molten copper with zinc and allow it to cool, that is brass. So brass is a mixture of, remember, alloys are mixtures. They're not compounds, they're mixtures. You're adding the copper to the zinc and you're just melting it and allow it to cool together, so that's a mixture. So brass is a mixture of what? Copper and zinc. Sorry, and we use it for making ornaments and buttons. Or, do you know what's ornaments? Ornaments are the things that we put in our living room for decoration, statues, vases, and so on. These are called ornaments. Or it can be used for buttons. These are buttons for the soldier's uniform, because the brass is bright yellow in color. So the yellow buttons that they have in a soldier's uniform, that is made of brass. The other alloy of copper is bronze. Bronze is a mixture of copper and tin. And copper and tin is used for making ornaments also. So both of them are used for making ornaments, but bronze is also used for coins. So this is the end of the chapter on extraction of metals. Please study it and try the questions that you have in your PDF version.